Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Rafida bin Abdullah with matric number 142365 and I will present about the electronic spectra of atom. So the structure of atom. As we know that the atom are very tiny size and the diameter of the atom usually around 1 angstrom. For example, helium atom has 2 protons and 2 neutrons. So atomic structure can be described by Schrödinger wave equation, which is Hamiltonian time wave function equal to energy wave function. So the formula of wave function is given is here. So where A naught equal to h square over 4 pi square me square, and the r is the radial distance from the nucleus, and n is the principal quantum number which I will explain later, which can have only integral values, which is 1, 2, 3 and until infinity. For particular values of r and n, psi naught and psi n square are simply numbers, and psi n square represent the probability of finding the electron at our chosen distance r. So there are 4 kinds of quantum numbers, which is principal, orbital, magnetic and spin. For principal, it governs the energy and size of the orbital. Orbital govern the shape of orbital and the electronic angular momentum. And for the value, for example, n is equal to 1, so the orbital value is 0 because n minus 1. So if n equal to 2, L must equal to 1, and so on. 3, L equal to 2. So next is magnetic. It governs the direction of orbital and the electron behavior in magnetic field. For n equal to 1 and L equal to 0, M is equal to 0. Next is 1. So from negative 1 until 1, which is negative 1, 0 and 1. For n equal to 3, M is equal to negative 2, negative 1, 0, negative positive 1 and positive 2. Next is spin. Spin govern the axial angular momentum and the electron, which given value only 2, which is plus half and minus half. And the motion of particle in space can be described by quantum numbers and probability. So this, if for L equal to 0 is S orbital, L equal to 1 is P orbital, L equal to 2 is D orbital, and if L equal to 3 is F orbital. So D is the region of the electron can be found in an atom. D, F. So for hydrogen atom, the selection rules, which is the rules that govern whether a transition is allowed or not, are N is equal any integer and L equal to plus minus 1. The consequence of this condition are that all transition from 1s into np, which is n larger and equal to 2, are allowed. For example, 1, 2, 3, 4. This is Lyman, Balmer. Next, Passion and P5 bracket P5. Okay, if from transition from Lyman is n equal to 1, up until P5, 5, and so on. Balmer start with n equal to 2. Partial start with n equal to 3, and so on. We know this in when we study both formula. Where n in the initial quantum number and n is the number of states resulting from the exertion of radiation, and R is the Rydberg constant. For each angular momentum L, there are two L plus 1 value of m sub L. The value of m sub L corresponds to the projection of angular momentum vector L in different directions. In the same manner, the spin angular momentum vector S can be also projected into S plus 1, which is into direction. Projection of L and S along the z-axis and the L sub z values of 1, 0 and -1 are shown in A, and S sub z half and -half are shown in B. This A and B. So the magnitude of orbital angular momentum L is given by the square root of L in bracket L plus 1 times h bar, which h bar is equal to h over 2 pi. Due to the interaction of two angular momentum, additional state result and the spectral line gets split into doubles and multiples. New selection rules have to be written in the term of angular momentum quantum number J, which defined as J equal to L plus S. The addition of these angular momentum are governed by special vector additional rules, the value of J and L plus S and L minus S. For each value of J corresponding magnitude of angular momentum, which in given by this formula, there are two J plus 1 projection. With the introduction of total angular momentum, a state is associated with a term symbol, where 2s plus 1 is the spin multiplicity, L is the magnitude of orbital angular momentum, and J is the total angular momentum. With the new selection rule, the early S to P transition, which was a single line, now gets split into two lines as follows. The splitting of line is called the fine structure of spectral lines. In this case, many electron atoms, the degeneracy of 2s and 2p and 3d and 3s, 3p and 3d, which was represented in the H atom, cease to exist, and the orbital energies are ordered as below. The filling up the electron in atom is done by using the Pauli exclusion principle and Hund's rule. According to Hund's rule, states with higher multiplicity are favored. The spectra of He+, which have single electron outside, are closed shells show similar spectra to hydrogen. They are referred as hydrogen-like spectra. In lithium, this part of the spectrum is similar to hydrogen, but the line arising from 2p state form compound doublets as shown below. When the ground state of an atom has more than one unpaired electron, as in the case of carbon, the spectra show a lot of complexity in the structure. Okay, that's all for me. Thank you for your time and attention.